In this chapter, we will see a current mirror and its biasing. So for the current source we have learned so far, this is its ideal current source has the characteristic of equal current over different voltage variation over a current source. Right? But reality for the transistor, if you use that for transistor, so for the voltage difference between drain and source and the current level, if you look at that, it will be only ideal current source within that inside the saturation. So below a certain voltage there, the transistor characteristics will be into the triode region and no more current source. So now the question is how to generate the proper VGS. But depending on the VGS, each current level will vary, right? For different VGS variation, our current level will change. So the most simplistic the approach you may think of is that something like the register divider things. You want to generate some value from VDD. Let's say R1 and R2. So VGS will be VGS plus minus. That would be what? So VDD times R1 plus R2 and R2. But the problem is, the VT varies, and supply also what can vary. VDD also can vary. For all these issue, and also the device process manufacturing error, so W and L will vary. All these parameters, all these things. Also, what can also vary? COX can vary, and mu. What else? COX can vary as well, and mu can also vary for different temperatures, right? Temperature. All these kind of things will impact on the current level. So I0 changes through the transistor. So this is not possible way to properly bias the transistor. So never use that. Never use this biasing scheme. And very bad. Okay. Very bad. But in the textbook, in the BJT device, in that case we are seeing many places using this kind of a register string biasing. For example, we have a BJT transistor and register string and R1 and R2, like that. Some load register, any load or whatever the the choice of the load condition there, G0, for example. In this example, the BJT case is a little different because we have a diode between base and emitter here. So VBE. But this VBE always approach to 0.7 volt. This is a very strong clamping, meaning for different variation of the R1 and R2, this voltage across R2 would be approximately 0.7, so that will create the voltage and current level through the R2, and the volt and current going into R1 and R2. So no matter what the VDD is, the voltage variation on the base is small. In that case, we can use this kind of we use this kind of a biasing scheme in BJT, but in the MOSFET case, we don't use this kind of a biasing scheme. So this is only valid in BJT, but still it is sensitive to PVT. So early textbook, they were discussing this kind of a biasing, but in the MOSFET we never use this kind of a biasing. So this is very bad. Never use, right? Okay. Now the question is, then how can we bias the transistor to make it work as a current source? Okay. To bias the transistor, we use, like, let's say we have a transistor MOS there. We need to generate the proper current. We need to generate the proper voltage to make sure that current is I0, for example. So that I0, this is I0. Let's just suppose we have somewhere ideal current is available. This assumption seems like a nonsense, but this is assumption for now. So there is somewhere else we have some current generator, current source is available. We want to generate the I0. To do that, we make our same size of the transistor with the diode connection. Then this transistor will flow through I0 current between drain and source, right? This is I0. To generate such I0, the proper VGS will be set up, right? So VGS, you can find that. So I0 equal to mu n half mu n COX W over L VGS minus VTH square, right? So proper VGS can be found, would be what? So VTH plus square root times 2 I0 over mu n COX W over L, like this, right? So proper VGS will find by that circuit. So once that is found, we connect that, we share that VGS with that device. Then we can replicate the current. This is current mirror. So voltage across this current source would be, let's say, V0. So as long as V0 is greater than VD set, meaning V overdrive voltage, right? So this is something that how we bias for basic circuitry. Once that is found, we can replicate this voltage right? To generate an additional current source. Many current sources can be generated. Let's say this is W over L size. Let's say in that case, I0 flows. What if we have a 2W over L, then it will flow to I0, right? What about this greater, let's say 10 times larger current? You make larger device size, then you can get the 10 times larger current level, right? So this is the way that we want to generate the current source. Now the question is the golden reference. So our assumption here, is golden reference and current I0 is already available. Okay, so we will learn about how to generate this golden reference I0 later, but for now we just assume that that is available. Okay, let's review the diode connected load shown on the left. So initially, we will see what happened when we apply these ideas in more detail. As you know that if you apply the current source over the capacitance, that would be CGS when this VGS is below threshold voltage, then we will see only capacitive. So X node, VGS node here, initially starting from 0 volt, VGS will rise up, right, initially, until this transistor turns on. So once the VGS goes above the VTH, then it starts, the transistor will start. But with this equation shown in here, second square law device model, if the VGS goes above VTH, then this will be overdrive voltage will be non-zero, right? Overdrive voltage will be greater than 0, so it will have current flows. But the pull-up current shown in here is greater than the pull-down current IDS, so it will continue to rise until it until it balance between IDS equal to I0, this current source I0. So IDS, if IDS equals to I0, then it will stop here and then stabilizes. In that case, the voltage over VTH is overdrive voltage that will set up the current I0. So this is how it works. And if you look at the VGS and VDS relationship, so because the VGS and VDS just same, it is operating from initially starting. So as we move from near 0 voltage to higher voltage up to VGS, final VGS, the current will increase like this, but actual the operating point will be where the VDS equal to VGS. So each operating point moving up along this line. If you look at closely the boundary condition, we divide the triode region versus saturation is that this condition, right? But this VDS, because VDS is always equal to VGS, this is always greater than VD set, meaning V overdrive voltage. So we can guarantee that this operation always guarantee in saturation as long as IDS is non-zero, I mean greater than 0, right? The existence of current on the drain and guarantee that this device is in the saturation. Okay. One thing that you can see that is that for the same gate voltage applied here, if you look at the slope here, the operating point Q, near operating point Q, there's a finite slope of the current variation that would be R1 over R0, right? In small signal model. Current mirror shown in here has the diode connected M1 and M2 in saturation. Make sure VDS2 must be greater than overdrive voltage or the VDS set, right? That's the same as the overdrive voltage. So as long as we satisfy that the current must be replicated by the device size ratio. For M1 is W over L, M2 is W over L times B. So the W width can be multiplied by B, or the L can be smaller, the scale down by a factor of B, but most of the case we scale W or the number of fingers by changing that we can implement B, right? So implement B. Why? Because if you have a different device dimension, then the device characteristic will change. For example, VTH will change for different dimension of transistor. So we want to make sure everything is in the same, has the same device model characteristic. So we just multiplicated unit devices. Okay, so in this case, so we know that the sharing gate voltage that would give us the VTH plus V overdrive voltage of the VGS, that's the shared. But to make sure that the exact current replication is only achieved by the same VDS between M1 and M2, because in realistic transistor characteristic it has the finite RO, the slope of the characteristic in saturation is the 1 over RO. So we learned that the RO is proportional to L and inversely proportional to ID, and you have a proportionality factor VE was introduced in this equation. So if we have a different VDS, for example, let's say M1 has the VX voltage on the drain, and M2 has the VY voltage there, then Vx and Vy has a different voltage, drain voltage, that would give us the delta I out, the current difference in the current mirror. So for example, when the B equal to 1, then this delta out can be founded by the drain so since we know that resistance or transconductance GDS conductance. So GDS is, we know that GDS is the what? ID over GDS is the 1 over RO, right? So we can find that the delta I out will be a voltage difference VDS2 minus VDS1 divided by the RO resistance, right? That would give us this first equation, right? This whole equation, right? So the RO, we use that, plug that, we had the first equation on the, let's say this is the second one, this is 1 and this is 2, so plug that 1 into 3, and then we can drive that third equation. Let's say this is 3 and this is 2, right? From 2 we can drive that 3 equation, right? So the here ID is the same as I out, right? I out. So using that fact, we can drive that current error. So to reduce the current error, it is important to have a large RO. To reduce current error, delta I out, RO must be increased, okay? So again, we have RO, and then the slope of from this curve is 1 over RO. So RO, we have written that the VE times L over ID, right? So if you write more in detail, so I mean the RO is also a function of VDS, so higher VDS, it might have a larger RO. If the VDS it get closer to triode boundary, then RO, the slope will be, RO will be go down, right? So that such factor can be modeled by the another term, that VDS minus V overdrive, right? So there's a factor that to increase the RO, the first method is a large L, right? But the large L results in what? Larger device size. Why? Because for the same, so if you wanna to maintain, let's say maintain overdrive voltage, so W over L, both W and L must be, right, increased, right? So in that way you can have the same current density over transistor. Why we wanna maintain V overdrive voltage? Because that also results in the sensitivity to the current sensitivity, current variation. We wanna have a large overdrive. If we have enough headroom, then the ID current variation to VTH variation would be small. So if you put too small V overdrive, then the meaning the W is very large, right? So you know that the relationship is ID half mu n COX W over L V overdrive square. For the given current level, if you maintain that the overdrive small, then you have to increase the size, right? So such kind of such kind of a decision will result in large parasitic ticks, right? CGS and CD and CS kind of things, right? So another method to increase RO out of a single transistor, so out of a MOS single TR. What else you can do? So you can do to the reduce ID. And so ID is small ID. Use small ID. Meaning if you use a small current level, it will be more flatter than the large current level. So the higher RO can be achieved. But this kind of a thing is limited by the circuit requirement. If the circuit requirement requires a larger current level, then you cannot change the current level. So increase the RO, you may have a smaller device, but for the fixed, this means that for the fixed fixed device size, this kind of requirement. If the device size is fixed, for example W over L, you cannot change this size, then smaller current level will result in large RO. So meaning ID goes down, meaning RO goes up, right? This is only useful you have a freedom of changing current level, okay? And also trying to maintain to have large VDS, meaning large margin to a triode region. So if your bias is too close to the triode region, let's say the region boundary is V overdrive here. So if the VDS is too close to V overdrive, then the RO will go down. So if you have a large range, away, if you place your device bias voltage VDS away from this boundary V overdrive, then you will get the good RO. Okay, so VDS, so try to large VDS minus overdrive, I mean VDS minus VDS set, right? VDS set is same as VD in scale model. VDS is similar to VDS set. So in that case, you want to have a large VDS, okay? So meaning VDS minus V overdrive. Okay. We'll have large VDS or VDS minus V overdrive. Large margin. This might be right way. So far away from triode region. Okay. Improving output impedance ROut is using the cascode device. We can use the cascode by staking another diode connected transistor on top. So share the gate voltage like this. So in that case, R out would be RDS of the bottom. This is RDS 2 and RDS 4. Or so the output is boosted by GM times RDS 4, right? So RDS is boosted by that amount. We can have this similar network by having different connection, diode connection. We have a negative feedback somehow, so it has the same output impedance shown on the right. But for the cascode output, although the cascode can improve the output, we are actually wasting large voltage headroom for signal, because if you look at this structure here, you require that the source node here, left and right, would be similar or same, because we are sharing the gate voltage. For example, B equal to 1, we have the same VGS for the different for those two devices, meaning those source nodes must be matched. So this node voltage would be 1 VGS, right, of the bottom device, 1 VGS, and then we have a VDS, right? But for the minimum VDS, for us to put this M4 in saturation, is that what VGS plus minimum VGS would be overdrive voltage of the M4, right? If you write it down in terms of threshold voltage and overdrive, then you have a 1 VTH plus overdrive of the overdrive voltage of 2 plus V overdrive 4, right? So this would be VTH plus 2 overdrive. So in this equation, you have a very large voltage drop is there, VTH factor there, meaning the minimum, this is V out mean, the minimum voltage they can have on the output here is quite high because of the VTH. For the low supply operation, it is important to have critical to have both high output and low voltage drop across the drain and source. It's important. So how we can avoid that? There's another way. So by staking this kind of a VGS step, so one VGS here, another VGS here, we have a 2 stack. On the right hand side is also same, 2 VGS stack provide us a very high small minimum V output at the current source output.